So today I'm going to be talking about the evolution of RAG. Let me see a show of hands. How many of you are building RAG systems or contemplating building RAG systems? All right, good. That's I would say 45%. Perfect. So I started with RAG specifically when RAG started, 2020. And in my team, we basically deal with production RAG applications, agentic applications, pretty much every day of the week. So we've seen the evolution of those from 2020 to today. And that's what the topic of today is going to be. If you need to contact me, bsb@redis.com. I'm also on Blue Sky, no more Twitter for me. And also, all of my code is on my GitHub repo, but also there's a lot of code on the Redis AI team and Redis main repo. I'm a Java champion, super proud of that. But this is not going to be a Java presentation. It's basically mostly Python for the code that I'm going to show you at some point. But really, it's more conceptual. And I'm a senior applied AI engineer. That's a very, very wordy title. They really didn't know where to put me. So they just gave me a title that made me happy. All right, so the agenda today. We're going to talk about naive RAG. This is basically how RAG started in 2020. We found out that LLMs would do things that we didn't expect, and we had to build some infrastructure around it, software infrastructure, to control the LLM's behavior. Then we'll talk about advanced RAG, how things have evolved over the years, concluding with modular RAG. Then we'll basically take a peek at the future of RAG. Where are things going with agents and all that stuff? If you were in my talk yesterday, you kind of have an idea of where things would go. And then I'll talk a little bit about Redis and RAG, just to basically do my sales pitch in that part. All right, so I love this quote because I started using this quote in like 2023, when it came out. But it's estimated that 44% of all of our businesses, activities, everything that we do is going to be impacted by Gen AI. In my job particularly, now I basically work with myself and a team of digital coding assistants to help me get stuff done in record time. Stuff that it used to take me a week, now it takes me a day. And that's just our jobs that they're pretty close to the technology. But in other places, for example, my wife uses Power BI, which is an analytics platform. And now they have an AI assistant built into the platform, and her job too has accelerated. So the things that would take her a week, now it takes her an afternoon. So everything is changing very fast, so we have to kind of keep up with it. So let's talk about RAG. And RAG stands for Retrieval-Augmented Generation. And it all started with this paper that came out in 2020. I think it's from Facebook Research, I believe. And the idea, again, was to try to control the behavior of this newfound technology called LLMs. And if you know your history, we have in the field of NLP, of natural language processes, language models for the longest time, since the 1960s. But the emergence of the massive amounts of data and the amazing computing power, and also architectures to basically train those, in particular the transformer architecture, basically changed the whole game. So now we have this thing that appears to be able to reason and can do amazing things for us, but it's unpredictable in a lot of cases. So let's actually talk about RAG. Let's talk about the generation part. By generation, we mean basically giving something to the LLM to complete. And that's typically the MO of an LLM. You give it something, and it's kind of the autocomplete of the future. But in our case, we want to basically give it a query and get an answer to the query. And it does that in a progressive fashion, basically. Finds like a small atomic piece of information that makes sense, then makes their inner systems in something like ChatGPT or Claude will basically make sure that that's formulated in a way that feels like an answer or the beginning of an answer. And then from that point on, it just unrolls down. It's like, how can I complete this little piece of the answer with more and more and more? And it has obviously a measure of completeness. Have I done enough to answer the user's query? And then that's the generation part of RAG. So you have a user query, And this is the simplest diagram in the planet. The user query, it's passed to the black magic box, the LLM. And then from there, we get also magic out of it. We get an answer. I don't know why I did this diagram. It's the simplest diagram. It's like probably if I were teaching this to high schoolers, maybe. But some of the things that can happen. Why don't we build all of our applications this way? Because this thing is unpredictable. Number one thing that everybody's heard about is hallucinations. LLMs can make stuff up. They're trained on world knowledge. And what that means is that you will have things like Wikipedia, which is pretty highly curated, but then you will have Reddit, where people will say the first thing that comes to their mind, sometimes just to pick a fight with somebody else. So you're going to have a lot of basically half-baked thoughts. You would have outright lies. You would have, obviously, hateful comments all over the place. And all that data ends up as the parametric knowledge of the LLMs. So with hallucinations, this is a funny example. This is an article in the New York Times where the a chatbot basically hallucinated. So if you're a good liar, what you do is you ground your lie on mostly truth. And then you put your lie in a very specific way that is hard to detect. That's what LLMs do sometimes. So in this case, I use a real setting, a real conference, and then made up a paper. So really bad things can happen if you outright blindly trust the knowledge coming out of an LLM. So you can see here that basically the conference was real, the article was not. ChatGPT just made it up. And if you've been using assistants on a daily basis, you catch them in lies all the time. Especially the ones that are multi-turn, they always work on a reinforcement reward loop. So they want to be rewarded for doing a good job. And sometimes to get that reward, they would make something up. They would do a lie. In my case, one funny example that happened to me, I asked coding LLM, which I'm going to mention, to basically create a wrapper around a database module in C that needs to be installed locally. And what it did is, at some point, it needed to run a sudo command to install this module, but it didn't have permission to do that. Instead of saying, hey, I need permissions to run a sudo command, or can you run this sudo command on my behalf? No, it didn't do that. It mocked the database in code. And then I ran benchmarks against the mock code. And I'm like, wow, this database is the fastest thing on the planet. Yeah, it was just a hash map in memory, So this is the kind of thing that you have to, these things will help you, but you have to keep an eye on everything that they're doing. And that's one of the reasons that we have things like RAG. Again, we talk about flawed data. You probably all heard the garbage in, garbage out principle. These things are trained with world knowledge. That means that we are not a very smart planet. So if you do the average, that world knowledge means mostly stupidity goes into an LLM. Again, I'm a big fan of domain-specific trained LLMs. So if you're, for example, doing medicine, an LLM that is trained with curated documents from the medical field, or financial documents, not with innuendos and half-baked thoughts and ideas. LLMs, just like programmers, when somebody, if you're a programmer and your boss tells you to do this complex thing that it's business specific, let's say you're in insurance, but you're a programmer, you don't want to learn everything about insurance. What you do is you're like, well, I've seen something similar to this. So I'm going to abstract the concepts, see what I have seen before that matches that, and then I'm going to go on with my abstraction, my own internal representation of those concepts without actually having to learn them well. And we know how that goes. Basically, you write some code, it works in your eyes, and then when you show them to the customer or you plug it in with other systems, it's like, this is not at all what we asked for. And that's what LLMs do too. They overgeneralize. Outdated facts, obviously, we know that training with LLMs has a cutoff in time. So if your question involves something that happens after that, and even it could be you're dealing with curated data and there's a retraction to an academic paper, that the LLM is using to ground its answer. Guess what? You're basically working with flawed data. So the cutoff in time basically means that the moment the LLM is released, everything that happens from that point on, it's completely unknown to the LLM. Lack of attribution. One of the problems when you basically do this type of thing, you work with an AI assistant of some sort, it's like it will tell you, yeah, this is, this concept. And you typically have to ask, it's like, where do you get that from? How do you know that? Can you give me a citation or a paper or an article, anything? And every once in a while, LLMs will tell me, sorry, I kind of, concocted that from a lot of different sources, but I don't have a real specific citation. And that's when I know that I have to go do my own research. So again, being able to attribute the knowledge to some specific entity, it's something that LLMs will have a hard time doing. And then context. Humans are really good at discerning context in a conversation, in a written word. Even we are amazing at context switching. Like, you and I could be talking about something, and then we're like, hey, and remember this thing that happened, and we talk about something completely different, and then we go back topic. So when you give a piece of information like that to the LLM doesn't know what the heck is going on in the middle. We have a term in Gen AI, which is basically lost in the middle. And that's what happens in large contexts. The LLM doesn't know how to prioritize all the information that it has. Even with the new LLMs that have very broad context windows, you still have the problem of basically having too much topic drift. So the topics change throughout the conversation, and the LLM has a hard time anchoring their knowledge. And of course, query complexity. The more complex the query that you give to one of these chatbot assistants, the harder a time is going to have to deal with it. So sometimes you have to, with the early ones, like ChatGPT, when it first came out, you would have to basically break your complex question into atomic questions that they could build upon. Now, LLMs have reasoning capabilities and planning capabilities. So they can take your poorly worded query and then break it into a plan. This is how I'm going to tackle this. I'm going to research this, then I'm going to summarize the findings of that. I'm going to use that summary to then hit this search engine and find recent articles. And so it creates a plan of how to basically approach the problem. All right, so now let's talk about the retrieval part. And so in RAG, the idea is that you want to give the LLM context about what's going on. And that's where we basically do retrieval. We do retrieval information from sources that we trust, sources that are relevant to the topic. If it's, for example, inside of a company, you might have a Q&A database. You might have a database of support tickets in the resolutions, so how something was fixed before. That type of data, we want to provide it in the context of, for example, let's say a support chatbot. Let's say it's a computer company, and you say, hey, my screen goes black when I connect to an HDMI adapter at GIDS. And sorry, just messing with you guys. And the problem is that you have to basically be able to curate this data, and you have to find out the optimal amount of data to put in the context window alongside with the user query and probably some other information of how to behave in this specific question. And you guys all seen like the system prompts for LLMs. As a helpful AI assistant, you are going to blah, 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 and try not to lie and answer the question without bombastic language. And you have to basically give it kind of a system prompt to guide their behavior. So retrieval. It's part of actually the field of information retrieval, which is older than all of us probably put together. And the idea is, in modern times, what we do is we get the query from the user, and then we hit some kind of database. Nowadays, we basically hit a vector database first, probably, to basically do a semantic search for relevant content that has been indexed already. But not necessarily has to be only a vector database. You can be basically hitting a SQL database with some SQL queries. And nowadays, there's systems where the SQL queries get generated by a smaller LLM based on the schemas and all that stuff. So the LLM knows how to write SQL queries on the fly for the specific question the user is asking. They could be document databases like MongoDB or Redis. They could be an all expert system that just happens to have an HTTP interface now. So you can go and ask domain-specific questions about the problem. So once you get your data, then you get that relevant information and you stuff it into the context somehow. Sometimes you have to do things like summarization, compressing the amount of information that you got. But again, the idea is to provide the LLM with relevant context. The same thing happens when you have multi-turn conversations. Because LLMs, you guys remember the movie Memento? The guy that loses his memory every 20 minutes or something like that? So the same thing happens with an LLM. The next question that comes along, it doesn't have context about anything unless you give it to it. So, and one of the things that I like to point out to most people getting into the field of Gen AI or AI in general, machine learning, is that information retrieval now has become super important. It's actually probably the most important part of it. The LLM advances and all that stuff seems to be going at a pretty decent clip, but knowing how to get the right data, how to collate it, how to prioritize it, it's super important. So I see this as RAG is just the tip of the iceberg, and information retrieval is the part that will basically sink your Titanic. That was a little dark, I'm sorry. So let's talk a little bit about vector embeddings before we move on to looking at the rest of the talk. So you have unstructured data. What do we mean on unstructured data? We mean data that basically is not in tabular form. It's not rows and columns with nicely known data types and a name for the column. We're talking about text, images, sound clips, basically EKG readings, all kinds of stuff that it doesn't have an inherent structure to it. So to do something with that, we have to find a suitable model first to encode it in a way that we can basically at least classify it or compare it to itself. So we have different models, like if you have images, you're going to use a computer vision model to encode your images into vectors. The way that happened, that came to be, is that most of the systems were classifiers. You basically give it a picture of a cat, and it will say, well, it's 80% probability that it's a cat, then 40% probability that it's a weird-looking dog. So it'll give you a list of things, of objects that has been trained on. So some genius, because this was basically a genius idea. Those typically CNN networks have layers, and in those layers, basically what we do is we compress the data in ways that at the end we have a classifier that basically will give you percentages for each one of the classes that it's been trained on. Somebody said, hey, why don't we just stop before we get to the classification part and grab the numbers that are in one of those last layers. And those numbers in that layer became vectors in this case. So you do that with a computer vision model, you do it with an audio model, you will do it with a text model. In that way you get vectors that can be compared against each other. So you use the LLM to create those vectors, and then you put the vectors in a suitable database. Redis. Wink. So now let's talk about RAG simplified again so we can have a bigger global picture. You submit the query. The query gets vectorized to, because you have to ask the question for retrieval in the language of vectors. So I vectorize the query, and then I find the relevant data in the database by doing a similarity search. So basically this is, imagine all the vectors are in this multi-dimensional space, and vectors that are similar are going to be clustered together. So what you would do is find the point where your query lands, and then look around it and collect the k nearest neighbors. And then you return that to the user, and then the user being the system, can determine which order to grab them in, whether the first one is more relevant than the last one, all that stuff. But you get a list of results that you can then use to basically put it. First of all, you're gonna get vectors back. So then you have to go and find the document that was created from that vector, or that vector was created from the document, to basically then take that text, English or whatever, and put it in the context for the LLM. So then you assemble the prompt. So the prompt again has multiple parts. One of them being the context that you retrieve from the database or any other system. And then finally, you can prompt the LLM. So one big question here is that there's two LLMs in this picture. This one doesn't necessarily have to be an LLM. If it's text, it's going to be an LM, a language model. But this could be a computer vision model. It could be a sound encoding model. So typically, we call this the encoding model. It could be an LLM, but it doesn't necessarily have to be. The one down there that basically does the reasoning and answers questions, it's an LLM, because that's the only system that we've been able to craft so far that can actually appear to reason over things. And then you give the answer to the user, and everybody's happy. Or are they? So again, the information retrieval on structured data goes into the LLM. We get embeddings. We go to the vector database. But let's talk about the indexing process too, so you guys get the whole picture of what happens. So when you have the indexing processes, you have your unstructured data. Let's imagine that it's just text, okay? It's a bunch of documents from a company. So imagine some enterprise documents from where the Coyote works. And, and those contexts, like, for example, if you've ever been in a corporate phone call for this boring, business meetings, you will experience topic drift. They start talking about something, and they talk about something else, and then they go back to the first topic, and they just keep on switching around. So you're going to have basically different topics embedded into the system. So we have to turn them into vectors. Vectors can only encode so much text into one vector. So we have to chunk the document. That means basically we have to break it into pieces that are large enough to fit into the compression factor of that vector or that model, and then vectorize them. So basically what happens is that you would grab some of the documents and create a chunk. The simplest way to do chunking, it's basically to break it into even pieces. But there's also semantic chunking, for example, where you basically track the document until the topic changes and see if that could be put in one single chunk, or grab that whole context that is the same topic and break it into chunks and then vectorize those. So you will have your chunks. Each of the chunks gets extracted, passed through the encoding model. You get your vector embeddings, and you put them in the database. So then at query processing time, now this is a little more than simple RAG. So now we're moving to basically see how things have evolved over time. So you have typically a rewriter, because humans are really bad at asking concrete questions. So what it does, it takes the query and tries to figure out better ways to basically word that query for the LLM. So you have a rewriter, you have a retriever. The retriever is, again, the thing that goes to the vector database to get context. Then you have a re-ranker. So sometimes the stuff that comes from the vector database needs to be re-ranked based on the query. And there's specific models that are good at re-ranking. So given a query and a set of results, put them in an order that makes the most sense for the LLM. Then you have something called the consolidator, which basically it's what it says. It just glues everything together. The reader, it's called the reader, but it probably should be called a writer. It basically creates the prompt with all the different parts, and then you get your response. There's the contextualizer if this is a multi-turn conversation, which means it has to basically put some information in there so the next piece of conversation can continue with what's happening. So here's an example that I use all the time. Imagine that we have an LLM that is about a chatbot that's about movies. And I ask a poorly worded question like, did Pedro Pascal had an animal nickname excluding Game of Thrones? Even I read that the second time. I'm like, what? So that would have to be rewritten. So then the rewriter, he's one of my favorite people on the planet. So then the rewriter will basically rewrite that query. So it would be something like this. List the movie role character nicknames related to animals played by Pedro Pascal in films or TV shows, excluding Game of Thrones. So you can see now, and we have models that are really good at rewriting poorly worded English or any other language. There's also keywords in here that are going to be used as anchors for the knowledge. So then the retriever is going to hit the database and get some information. So it's going to get a few articles from this database. So there's articles about different movies in there. And you can see that in the last movie there, Triple Frontier, Pedro Pascal had a nickname of Catfish. So it's an animal nickname. It's not Game of Thrones, and it's Pedro Pascal. So kind of we hit all the items that we needed. So the re-ranker is going to reorder those appropriately. And obviously, it could be hundreds of results or just a few like this. Then the consolidator, it's going to take all that and glue it into a nice block of text for the LLM to understand. And this includes some extra information that researchers have discovered that it helps the next set of steps. So you're going to do follow-up questions. Maybe you already answered the follow-up question, or you have enough context now in your context window to be able to provide a richer answer on the next turn. And then you get your response. You get the prompt generated, which basically has the system prompt that says, hey, generate a concise yet informative response, and it gives the context and typically some other things in there. But that's what you send to the LLM to basically get a response. And then the response, depending on the type of chatbot system you're using, is going to try to make it feel very human to you. It's like, yeah, sure, Brian, here's the answer, you know. Okay, and this all looks simple and easy, but this is how things begin with RAG. And then you basically try to cross the bridge of real world deployments, and you get to that scary world on the other side. This is one of the diagrams that our friends from LangChain basically put about RAG. So there's things like construction, retrieval, query translation, routing. I'm going to talk about all of those in the next 30 minutes. So don't get scared by that picture. You know, if you break it into small chunks, it's all understandable. But if you're new to the field and you basically jump into this and try to do everything at the same time, you're going to regret it. So I'm going to skip this slide because this is more corporate stuff. But yeah, the path to production is not an easy one for RAG applications or agentic applications. I'm not telling you that to basically detract you from trying, but you have to be, all the principles of good software engineering and architecture still apply. Just because the LLM can do magic tricks doesn't mean that everything else goes out the window. The LLMs kind of end up living in modules or nodes of your architecture, and you still have to, you're going to get amazing things out of it, but you have to put fences around it so they basically behave correctly. So let's actually recap naive RAG. So very simple. You have documents. You index the documents. Those go into the retriever. You can retrieve context, create the prompt with the prompt for the LLM with prompt in context, pass it to the LLM, get a response. All that from a user query. Now, typically what happens is you have text extraction. So this is the part that they don't tell you. It's like, oh yeah, you remember OCR? Anybody's done OCR? Given it's gotten better, but optical character recognition, basically recognizing written text, handwritten text. So you have to convert everything to a format. Typically, just plain text would do. PDF is okay because we have a lot of PDF readers that can take extract the information from PDF. But you have to basically do a lot of this. Convert the formats. You have to, OCR for scanned documents, and cleaning and normalization. Documents in different formats have a lot of metadata, have a lot of things that are irrelevant. Like, for example, if you were to go to the website Medium, where you have articles, there's always a whole section of ads and other articles completely irrelevant to the content in there. If you were to print that as a PDF and then put it into an LLM, you're going to have a lot of garbage that's going to go in because of the end tail of those documents. So all that document data has to be curated carefully. Chunking strategies. So we talked about chunking. The typical one, it's fixed size chunks, but this is kind of all RAG. We found that when you do chunking, you want to overlap them a little bit. So the next chunk has a little bit of the prior chunk, and that seems to keep the semantic chain more intact than if you just basically break them evenly. There's also obviously sentence level chunking, semantic chunking. Typically humans, we tend to stay with one thought in one sentence, not all the time, but that proves to be correct in a lot of cases. And then embedding creation. Early models use very simple sentence embedding. You probably heard about the BERT models. There's always some kind of Sesame Street character associated with the model. And they have, pretty low dimensionality. 768, it's one of the magic numbers of embedding sizes to 1024. And you get basically 1 to 20 vectors per second in terms of the computational requirements of the system. So now, index and retrieval in naive RAG, we kind of talked about this. I'm just going to put it in here so you can see that. But remember, we talked about basically the top K relevant chunks coming out of the system, and then you have to go and look up the data that created those chunks so you can provide that text or images or whatever it happens to be. So what are the technical limitations in here? Context windows. LLMs have you can call it a memory. A memory per interaction. And that memory, it's limited. So you can only have so much in there. Typically what's in there, it's the parametric knowledge that the LLM thinks it's gonna need for that specific task. So it's typically limited to tokens. In the world of LLMs, tokens are typically either a word or a sentence fragment. It varies from model to model. And we talked about the lost in the middle phenomenon. The bigger the context gets, the more things in the middle are basically going to be ignored. And it's kind of like the way humans interact. If you and I start talking about one topic that we're both interested in, at the end of the conversation or tomorrow, we're going to be like, hey, yeah, Bill, we started talking about that thing, but we ended up talking about this other thing, and I don't remember anything that happened in between. So LLMs seems to have the same behavior, observable behavior that humans have, that they basically lose track of the stuff in the middle. There's also semantic relevance challenges. The mismatch between the query and the docs. So sometimes, even though you use semantic similarity to basically try to find queries that were similar to that, humans, like for example, the way that I would talk about some subject is very informal. Okay, but I might need the information from a formal source, like an academic paper, which are written to sound more important than you are. Therefore, there's a disconnect between the way that a question will be worded and the way that the document sources of information are worded. So that semantic mismatch, it's typically an issue. We talked about topic drift within the chunks. And for example, LLMs have a horrible time with numbers. They're getting better. But before you could say, hey, it's 2 plus 2, and it'll be like, hey, 5. And we didn't know why they couldn't do simple arithmetic. So now sometimes there's tool calling when they detect an arithmetic expression or operation. Rather than the LLM doing the math, it basically goes to a specialized tool that says, hey, I am a calculator specialized tool, and I will add those numbers for you and give you the answer so you can give that answer to the user. And we have, obviously, quality and consistency issues. Sometimes you will go to ChatGPT the next day, ask the same question, and get a different answer. Even though they're trained with a cutoff of data, it was all the same data. The training didn't change overnight. You're still getting a different answer. Everybody's heard the term temperature in LLMs. So it's kind of like a little knob that basically allows the values coming out of the LLM to be randomized a little bit. So we can foster creativity. That could be a little dangerous. So yeah, I typically keep the temperature pretty low on my LLM projects. So with quality and consistency, you have like context-related hallucinations. We talked about hallucinations already, inconsistent responses. And then every time that you have a complex multi-turn conversation, things get more and more, like they start degrading slowly until you basically get to the point that it's like, I have to start this conversation again because it's going nowhere. And then performance. There's a overhead to embedding the query that's coming in. The more powerful your embedding model, the typically longer it will take to embed. Therefore, having a good retrieval system is important because at least you can sometimes bypass the LLM by getting information from a cache. And token consumption costs. Many a startup that basically started with a Gen AI platform and offered a free tier, went bankrupt because you're basically, donating all your money to OpenAI or, Anthropic or one of them. So chunking dilemmas. The optimal chunk size will vary by the type of data. The complete context completeness versus retrieval precision, and we kind of hinted at that. And the, basically how many tokens typically are thrown away on each one of these turns that actually might not be fulfilling any or forwarding the progress of the answer. So behind the scenes, the LLM is trying sometimes, the LLM or the agentic system that's running the LLM. So when you use ChatGPT, for example, that is just not an LLM. That is a complete agent-based system that has tools to call different systems, to help it with different things. And while it's doing that, they're basically cranking those tokens like you're at the gas station. The problem is that you don't see them until basically the answer comes back. So we have the difference between all the different documents that are used to basically deal with the retrieval. So for example, you have technical documents versus conversational documents, domain-specific terminology, multi-model content handling, and again, the embedding model, it's very important. General versus domain-specific models. I'm a big fan of domain-specific, smaller models to basically anchor things better in the domain that you're dealing with. 15 to 45 performance variance based on the model. So that's a big, if somebody will say, if you replace the specific module in your software, it's gonna be 45% better. That's significant. So picking up the right models for the task, it's super important. And obviously you have the RAM and disk cost of all of this stuff. That's always going to be a factor. Okay, so now let's talk about advanced RAG. How have things changed based on all the different problems that we ran into over the last 5 years? So this is a much more complex diagram. You have query processing at the top. You have query expansion. You have query rewriting. So there's a lot of manipulation that happens to the query now to basically before you hit the retrieval step. When you get to the retrieval step, typically we just don't go to a vector database alone. We might go to multiple vector databases in other systems to create a collection of knowledge that it's going to create a better answer or a better context for the LLM to answer. We talked about re-ranking. We also have a context processing. So after everything's put together, there's other models that now being trained to spot flaws in that whole prompt that's gonna go back. So before you send the prompt to the LLM, this other model is gonna basically review it. So imagine it's the manager at the factory with the checklist. He's like, yes, oh no, let's fix that. So it's a much more complex chain of events. Then you have things like context compression. So once you have the context, it goes to the LLM answers. Now you have the same context as before, something else gets tagged onto it. It keeps on growing and growing and growing. At some point, you're gonna have to defrag that. You have to basically compact it. So techniques like summarization, basically looking for keywords and finding concepts that might be expressed in a shorter way too. So there's a lot of basically compressing and compacting of the context. And then finally, you end up building your prompt, asking the LLM, and get an answer. So we talked about hybrid search. This is a big topic right now. So for example, there's keyword search like we've done for many years, but there's also full text searches with things like BM25. So now the idea is to basically do one query against, for example, let's say a vector database that can do vector similarity searches and full text searches like Redis. And what happens is you have now a single query that's called a hybrid query, where you can basically say, I want you to give different parts of the answer different weights. So the vector part is going to have this much impact on the answer, and the full text search will have X percentage of the impact. So then you can use that to create a better set of retrieve context. We talked about all the post-retrieval processing, so re-ranking, synthesis, and compression of the context, and the improved prompt engineering. So prompt engineering has become a science of its own now. Once you have a prompt that you think is good, there's still systems that can go through it and be like, yeah, it could be better. So we talked about the pre-retrieval optimizations. Now you can basically have a query analyzer that analyzes the user's query and creates multiple subqueries. And then in parallel, because a single query might be too complex, too wordy, and mixing multiple things. I do that all the time with LLMs. I'm like, hey, can you tell me about this thing and also tell me about this thing and how they relate to each other and this other topic? And that's like 4 questions in one. So what the good query analyzers will do now, it's break them into subqueries, hit the retrieval system for each one of them, and then assemble a better answer from all the individual, more targeted questions. So the hybrid search, again, you have query analysis. So you would do your vector search, which is a dense vector retrieval. Then you would do your sparse vector searches, or mix them with something like full text searches like BM25, and also do exact keyword matching. Because sometimes, just finding that specific keyword will give you the best chunk of information to provide to your system. So then we fuse all that together. So there's a reciprocal rank fusion. It's a technique that basically we use to combine information from multiple systems. And then we get a final retrieval set, and then we can do a re-ranking with that. I don't know where that last arrow goes to, but so we talk about re-ranking. There's multiple approaches to re-ranking. There's cross-encoders. Those have shown to be 15 to 30% more accurate, but they're 5 to 10 times slower than bi-encoders. And you don't have to really know what these are, because but there's choices out there. So depending on, for example, if you're dealing with a system where you're putting a message in a queue, and that's going to go to a system to get an answer, and the answer is going to be sent via email, then I don't care about being 10 times slower. I have the time. But if it's a chatbot where you need an answer immediately, then you probably want to use a smaller model and a cross-encoder so you can basically get an answer. Sorry, not a cross-encoder, a bi-encoder so you can get an answer quicker. In some of the systems now that are in enterprises, we basically say, hey, here's what I found, but I will do more research and send you an email with a more complete information. So you can basically get the best of both worlds if you want to. So context synthesis, it's basically how to combine things together. So you can basically do LLM-based document summarization. So before you basically stuff a document into your vector database, you chunk it and stuff it in there, summarize it with an LLM that would basically grab the important information, synthesize it, and condense it in a way that basically it's more effective for the system. Plus, you're spending less in memory, disk space, and retrieval times are going to be faster because you're dealing with less data. Also, citation and reference tracking. So now every time that we do chunking, for example, there's a pointer to that chunk of where it came from. So when we assemble the question, then we can look at all those pointers and say, okay, here's the list of references where that data came from. Which, for example, in the medical field, or if you have like a financial advisor bot or something like that, you probably want to know where that came from. Because hallucinations could be deadly or financially catastrophic in that case. In a context compression, there is basically elimination of tokens for non-essential content. So again, you can basically look at some of the text, and the LLM doesn't need full-blown sentences like we do. You can drop connecting words, a bunch of different stuff, and end up with basically nouns and verbs and adjectives, and that will be more than enough. So there's a lot of token elimination. Basically, there's a system called LLM Lingua that gives you 30 to 40% compression in basically your data that's going to go into your vector database. And also highlighting. So like you remember when you were in school and you got a book, and you got your highlighter, and it's like, highlight the parts that are important. This is the stuff that I need to know. And sometimes in a page will be only like 2 or 3 lines that were highlighted. So there's the same concept applied to this information. Basically, highlight important things. Some of the other stuff can be either secondary or ignored completely. All right, so there's re-ranking approaches, context synthesis, and context compression. We talked about those. Great. Now, this is something that we actually do at Redis heavily, and it has saved countless amount of tokens and money to our customers. And it's called semantic caching. So the idea is that you have a user query, you create your embedding for the query, but then you do a semantic search again, a cache. So if somebody asks the same question or a similar question before, you have it in your semantic cache now. So you can do a cache lookup, and if it's a miss, then you're gonna do the normal thing. You're gonna go basically execute the full RAG pipeline and then store the result in the cache, okay? Then return that to the user. If it's a hit, you can return the answer immediately. So we're talking about, milliseconds versus sometimes full-blown seconds. And the cool thing about this is that some of the things that we've done, it's basically keep statistics on the cache keys. So if there's a specific key that gets hit over and over and over again, it's an important one. What you can do, it's on the background, you basically grab the context of the cache and you make it better. You use that context of the cache, that answer that's cache, and basically pass it through LLMs and further research to create a better answer to replace that entry in the cache. So now your cache is getting curated based on the importance of the entries. So your customers are going to get better answers out of the system and in record time. So now let's talk about this is kind of where we are right now, modular RAG. And what we have now is we have a routing kind of model, a routing system at the beginning of the whole pipeline, which basically allows you to go in different directions based on the query. So sometimes it would be a knowledge query. So a query that you need the parametric knowledge of the LLM to answer. And in that case, you're going to go to the normal RAG, basically pipeline that we just saw. But sometimes it's a conversational query, so it relies on context. So then you have your context in a short-term or long-term memory. You can use that context to answer that question better without having to go to the full LLM. Just here's some information, assemble an answer from this information. So you still might use an LLM to assemble the answer, but you don't have to incur the hit of basically doing the multiple looping to basically create a full-blown synthetic answer from the LLM. You also have specialized queries where the query might be so domain specific that either it's already on your cache or it's on a Q&A database, for example. And this router, it's a semantic router. So basically, it will look at the meaning of that question and be like, this looks like something we can answer with a Q&A database. So just send them there directly. Save yourself all the token cost of going through Anthropic or OpenAI. So modular RAG architecture. So there's been a transition to basically this modular approach. So now they're all plugin based. So for example, your re-rankers, you will have a menu of re-rankers to plug into your pipeline. You would have different models for different things. So you can basically say, for images, if the images are this size, I want to use this image model. If they're of this other size or high quality images, then I want to use a better model for this specific problem. And all those components are like Legos now. So you can basically mix and match how you want your pipeline to behave. And basically, still, these are not generic systems. The thing that people fail to understand is that these are very highly specialized systems because you have a highly specialized task to do. You're not building a ChatGPT. You're building something for your company to maybe answer insurance questions, banking questions, and that means that specialized knowledge in domain has to be taken into account primarily, not as a secondary thought. So the benefits of this modular architecture is that you obviously have flexibility for different use cases. Plug in the right components base. You might have two chatbots in your company. The same architecture, but different specific components based on their purpose. So easier maintenance and updates. Now we have protocols and guidelines of basically how to connect different parts of a RAG pipeline. and we can do basically a lot of component level optimization and specialized tools and data sources. So when you jump from complex RAG to an agentic RAG, then you're going to have tools that will allow you to basically improve the answers that are coming out of the LLM or the results of the process. So this doesn't have to be a chatbot. That's another thing that I want to point out. This might have no humans at all until some report appears at the end. So if you think only of conversations and chatbots, then you're going to miss the bigger picture of this system. They can do a lot of things that before require a human in the loop before. It's like, so now it's basically the next stage of automation. And we're almost there. All right. So in one of the things that we've done at Redis is basically we have a search module that allows you to basically do multi-source retrieval. Oh, let's forget about that. But parallel query strategies. So any retrieval system you have, make sure that you can basically ask things in parallel. So you can get multiple answers and then assemble them and not have to do them in sequential order. We talked about reciprocal rank fusion, a very powerful technique, multi-vector retrievals per documents, and a way to do an ensemble of those things coming back. In some of the vector search optimizations, right now we have different ways to index a vector database. So flat indexing was the normal one, basically where you index every vector in the database, and what happens is you have an ON kind of a performance signature, and N being the number of vectors in the database. So when you're talking about some places that have billions of vectors, this is not a good thing. So we have something called HNSW, which is a hierarchical navigable small world, which is a way to vectorize things, to create an index of the vectors that it's much more efficient, smaller, not sometimes not faster, but definitely smaller and easier to navigate. And being able to, one of the things that everybody basically misses, it's like, okay, I vectorize all this data, and I have vectors now and everything works great, and then some documents have updates. So what do? You have to revectorize them. How do you detect those changes? How do you trigger the revectorization? Also, the same thing happens when the model changes. Sometimes a model would basically be improved. It's like, well, you have to revectorize everything. Can you use the old vectors to vectorize to get the new vectorization parameters? That's a technique that we're working on right now. Or do you have to go take the whole text again and revectorize everything? So in my experience, it's better to have an active system that detects changes and vectorizes things as they happen in some kind of background queue. But if you have to go like if you're a company like, let's say, Walmart, and you have all of your products vectorized, and something changes in the model, then you're going to have to run vectorization on like multiple machines in a data center, and watch the lights dim and the electricity in the city be scarce. So again, this is something that you have to keep in mind when you're doing these systems. Now, there's also memory and contextual awareness. So systems that are conversational or multi-turn, they need a short-term memory to deal with a conversation, and they need a long-term memory store to basically learn from the past. So you want to basically learn from the history of the system. Things like recent conversations, so having timestamps on things, it's important too. If there's 5 answers to a question about some tech support issue, you definitely want to get the newest one, because your products might have changed. Even the same product name might be a much more advanced model now. So the answer that it's the oldest might not apply anymore. So that temporal aspect has to be taken into account. 3 minutes. All right. So I'm going to skip through this. So again, we talk about one term to actually think about. It's episodic. So basically, like what I just talked about, time-bound interaction sequences. And then short-term and long-term memory, it's really easy to relate to, because that's how kind of we humans work. We are a memory provider. Obviously, that's our thing. We basically provide all the semantic search, all the vector database. We are the faster vector database, bar none. If anybody says otherwise, tell them to come and prove it to us, because we have put the benchmarks out there. And you can store JSON and hashes, time series, Redis streams, all the vector-based stuff. So the next little step in here, it's routing and orchestration. And again, this is basically how to have that router again and take you to specific places that actually match the query that you're sending. And now let me see where we are. So I'm going to do a little bit of skipping here. Yeah. So some of the new RAG patterns that you're going to see in there are rewrite, retrieve, and read. So basically, you reformulate the query heavily. So you spend more time curating the query so you don't waste time when it matters, which is the time that you send it to the LLM. And that has proven to give you a 25 to 35% improvement in the relevance of the stuff coming out of the retrieval system. So if you have if it's a human-driven chat interface, this is definitely going to be something important to take into account. Generate and read. Basically, instead of creating or trying to retrieve context, a specifically trained LLM will take the query and synthetically create context. Which, yeah, sounds strange, but it has proven to work fairly well in specific cases. So it outperforms the retrieval for some specific question types, and it reduces the dependency on external knowledge. So, and again, you can always make decisions on the fly. Does this need to be answered immediately? Go this way. Do we have time? Then go the long route. So it's one of those things that you have to basically measure everything. In interactive retrieval, again, that's another technique to basically continually retrieving information based on things like the contents of your cache, the historical set of conversations. And we are out of time, but let me, I want to show you one last thing in here. So, and if you went to my agentic systems talk yesterday, you probably got a lot of that information. But again, this is the summary of what has happened. Original RAG paper happening here, basic vector retrieval, simple prompt augmentation, now vector database optimizations. Now with the advanced RAG that we saw there, that's kind of the standard for a while. And now we are in the modular RAG era. Also multi-modal RAG is becoming very important. So images and text and sound and things from sensors all together to basically come up with a holistic answer to something. And the holistic answer might be changing the temperature in your thermostat. So it might not involve you at all. You might say, hey, I want to find this balance between energy consumption and comfort. And you let the system basically figure that out for you. Nest kind of does that. Not to my comfort, but it does it. So again, agentic frameworks, multimodal RAG, hybrid RAG, long context. Contexts are getting wider and wider and wider. So you can do more with them, but at the same time, that lost in middle thing still happens. And just take a look at Redis for some of this needs, because we do a decent job there. If you want to, I have a QR code in here for you guys to go give it a try. They make me do this. Thank you.